Okay, so this is a brief presentation of my project for 178 ECE 178 embedded systems at Fresno State University. I'm going to briefly go over the Altera IP cores that I've used in this hardware system design and explain the purpose. So I'll begin with these two speakers, and basically they're just a simple circuit of speakers with an AND gate. And the AND gate has two inputs. One input is from the voltage from the general purpose input-output pins on the DE2-115 board, and the other input to the AND gates is the control signal used to determine when power is allowed to the speakers and when power is not allowed to reach the speakers. And so by writing a 1 or a 0 to this control signal, we can basically perform pulse width modulation to control the frequency of the speakers. And because the signal is copied to both speakers, the result is essentially stereo. In addition, over here, we're reading from an SD card. We're reading words from a text document on the SD card. And here we have also a connection to a PS2 keyboard, which will be used to get user input, which you see here. And the last IP core that I used was the VGA controller IP core, in addition to a number of other video-related IP cores that were necessary to basically send a cascading streaming bit signal that would be modified and then mixed between a character buffer and a pixel buffer in order to basically mix the alpha blend the two channels so that we could have text on top and colors on behind on two separate layers. So the actual project itself is a word scramble game. And what happens is the user enters a word trying to unscramble a word that is read from the SD card and scrambled and displayed to the screen. So there's also audio, which you will be hearing in a moment as soon as I start it. And I will begin it by pressing a key. You see the animation plays there for a second. Sound plays, and now we're unscrambling a word. In this case, the word is 10. When it's successful, a green check mark is displayed across the screen. In this case, the word is basis. Now suppose we enter the wrong word. An X is displayed across the screen. And this goes on for a while, as long as there's words on the SD card to be read from. You can see that there's a time limit listed right here that runs down. If it's allowed to run out, then the out of time message is displayed. The score and the attempts is also displayed, but there's a little bit of glare, so that may be a little bit difficult to see. That's a little better. You'll notice that the sound cues for actually typing on the keyboard are actually randomized, whereas backspacing, for instance, is a constant low frequency. So basically, that's the extent of the project. When it comes to actually coding it, it took a little over 1,000 lines of code to actually get all of the different IP cores working together and the entirety of it working in sync properly. Some of the bigger challenges I ran into were compatibility between different IP cores. One specific instance was when using the PS2 keyboard and also trying to buffer pixel data information from SRAM, I ran into a problem where basically, or buffer pixel information from the SDRAM, I ran into a problem where it just wasn't getting to the screen fast enough. through the buffer. And after reading through the documentation, I discovered that the problem was that the DMA for the buffer, the direct memory access, and the processor were both essentially competing for access to that SDRAM memory. So in order to fix that problem, I had to install SRAM or define SRAM in the system parameters in QSYS, set up those connections, export that hardware description language, Verilog, and make sure that the system was ready to actually use SRAM. Then I was able to use SRAM exclusively as the memory for the pixel buffer. And that allowed the processor to gather instructions exclusively from the SDRAM memory. And that solved the problem of the DMA and the processor both attempting to gather pixel data or their relative instructions or pixel information from the same memory at the same time, because they were now using separate memories. This increased the efficiency and solved essentially my major problem. But then after that, it introduced a new problem, which is that the PS2 keyboard was no longer being sensed. And this took me some time to figure out, but I discovered that it was my changing of the processor type from standard to fast that caused it to be unable to pick up the keyboard unless I increased the timeout of the keyboard keys in the header file. So these were some pretty confusing and challenging issues to debug, but when I got them solved, I was able to get it working pretty well. One other thing I'd like to point out is that, interestingly, because there's no multi-threading in this program, we actually can only control and actively use and test without more complex structured code. We can only test a single interval timer at a time. And so because of that limitation, and because of the fact that the interval timer also has to be used to drive the signals to the speakers to control the frequency of the output, there's a problem where typing on the keyboard can actually cause the time to be offset of the amount of time left, because they both are counting from the same interval timer. And so in order to fix that problem, what I did was I introduced a regular decrease to the time left per a certain number of key presses. And this just served to make sure that although the timing itself wasn't perfect, at least it guaranteed that if someone continued to press the keys, they weren't able to pause the time left timer indefinitely. It would continue to count down regardless. That's essentially the entirety of the project. Thanks for watching and listening.